Merci de ces mots gentils. Et pour moi, c'est un grand plaisir d'être ici et je veux remercier le jury de m'avoir invité de donner ce cours. Et comme M. Léon l'a dit, en fait, j'ai longtemps hésité de le faire en français ou l'anglais, mais finalement, je crois que c'est mieux pour tout le monde que je le ferai en anglais. The topic of this course is called the BKT transition. And the BKT transition, of course this name doesn't tell us so much about what we're actually going to talk about, but this is about a phase transition in physics. And the goal of today's lecture is to explain a little bit what's going on with this phase transition, what is the physical point of view, and hopefully at the end we will see a little bit of mathematics on, how can we sort of understand this phase transition mathematically. So I told you that we're going to talk about the phase transition. Today's introduction. And so first, what do we mean by phase transition? So I think we are all familiar with phase transitions. So for example, when you have water and you cool it down to 0 degrees Celsius, it turns into ice. But we can ask about the way that it turns into ice. So actually you can do this experiment at home. And it turns out that when you cool a bottle of water to just below 0 degrees Celsius, it can still be water. But then you can sort of tap the bottle. And this tapping of the bottle creates a tiny place for the crystal to grow. And in fact, the bottle will turn almost instantaneously into water. So we know that into ice, of course. So yeah, you can have a sort of crystallization percentage if you want. And if you're above 0 degrees, you're 100% water, and then when you go below, you're 100% ice. Of course, I'm doing everything the wrong way around. So this is the crystallization percentage. So another famous physicist, a famous physicist did an experiment where now he wasn't looking at this phase transition, at water, but rather to magnets. So this is Pierre Curie, and he is famous for the Curie temperature. And he asked the question, suppose now that I take a magnet and I look at the strength of the magnet on this axis and the temperature. Then each material has a special temperature, which is called the Curie temperature. And above this temperature, the magnet stops being magnetic. So now we can ask, suppose we take a temperature below the Curie temperature, how does this magnetic strength behave as we approach the critical point? So in fact, what he established experimentally is that the temperature drops continuously to 0. Okay? So really the magnet loses its strength, and when you get to the critical point, you already almost lost all of your force. Okay? So what I want to stress is that there are many forms of phase transitions in physics, and there are some qualitative differences between them. Here, the phase transition is very sudden, and here the phase transition is somewhat continuous. Okay? And of course, the goal of mathematics is to create mathematical idealized models which exhibit this kind of behavior. So you can start with one model, look what the phase transition looks like, and then you can change the model or make it more complicated in order to model other types of materials or other types of phase transitions. So the model that I am going to present about is called the XY model. So what is the XY model? In the XY model, we always start with a simple graph. So a collection of vertices and a collection of edges. And on each vertex we place a spin. So the spin is a random variable, and this spin points in some direction. So we can think about it as a sort of compass needle. So in a second I will define rigorously what we mean by the XY model. So in principle the spins are random, but we introduce a force, and this force makes that the spins that are close to each other, so that those ones, for example, they are next to each other, they want to point in the same direction. So there is some randomness involved, but they also have this preferential direction. Okay? And okay, of course, this is just a small example, but in practice, what we do is that we, as the graph, we take a representation of space. So the actual graph that we work on doesn't look like this, but for example, if you want to model two-dimensional space, we would take a graph like this, where at each vertex, so you put a spin, and then the spins that are next to each other, they prefer to point in the same direction. Okay. So how do we define this mathematically? Formally, we have this graph, and we take a family of coupling constants. So this is a family of numbers. Indexed by the edges. And each number tells us how strong is the coupling constant, how strong is the interaction between those two edges. And formally we define a probability measure, and this probability measure is defined as follows. If we take an observable A, then its expectation is defined as the integral of A of sigma, e to the minus Hamiltonian of sigma, d sigma. And then there's the normalization constant. So, yeah, of course I didn't yet define the Hamiltonian. So basically what happens here is that we have a sort of background randomness. This probability measure is the Haar measure, and it tells us that the spins want to point in a uniformly random direction. And then there's the interaction potential, which kind of tells us that, well, when h is very low, this number is going to be large. And yeah, it means that spins that point in the same direction are going to be more likely. So what is the Hamiltonian? The Hamiltonian is going to be minus sum over edges, inner product sigma x, sigma y, where sigma is a function from V to unit circle embedded in C. There's the coupling constant. And here the inner product is just defined as the inner product as a subset of this two-dimensional space. Okay? So what it means in this picture is that the configuration sigma tells us that we have a spin at every vertex. So at each vertex sigma we have a spin, which we call sigma x. And in principle, I'll use another color. This is the Haar measure, so this means that in principle all spins, they kind of point in a uniformly random direction, independently of each other, right? So for each one, you kind of well, if you have a real compass, you can kind of imagine that you spin the needle and it just randomly ends up somewhere. And now what this Hamiltonian is telling us is that we're going to measure the inner product between spins that are next to each other. So if you have two spins that are next to each other, this inner product is going to be big. Now if you have a big inner product, the Hamiltonian will be smaller. And if the Hamiltonian is smaller, it means that your weight or your Radon-Nikodym derivative is larger. So configurations where spins that are next to each other point in the same direction, they're going to be more likely in this measure. Okay. So in practice, in fact, usually we take the j's to be constant. So we take all the j's to be beta. And we think about beta as the inverse temperature. So for example, if beta is 0, if all the jx's are 0, then this thing becomes identically equal to 0, which means that this whole factor vanishes. And we're just looking at, all the spins behave independently. Now, if beta is very large, so that means that the inverse temperature is large, so the temperature is small, then it means that this factor is really big. It means that we're a lot penalizing when neighbors are in a different direction. So for example, if beta equals 0 and we take a sample from this probability measure, then we can imagine that it looks something like, well, it's completely random, right? There's no correlation at all. And if we take beta very large, then we expect that neighbors point almost exactly in the same direction. Okay? So there's really a difference going on in terms of, well, do your spins decorrelate or do they point in the same direction? Okay? Now, if you put this model on a lattice, like the square lattice, then we call it a spin lattice model. And in this case, in fact, we still have some freedom in the definition because we can look at a two-dimensional lattice or three-dimensional lattice. And in principle, the physical behavior of this model should depend on the dimension of the lattice. And in this talk, in fact, we're going to concentrate on the dimension 2. So we will always work with a two-dimensional lattice. So what we want to do is well, the ultimate goal of this course is to understand or at least prove the existence of this phase transition, which is called the Berezinsky-Kosterlitz-Thouless transition, which was, well, theoretically predicted by Berezinsky and independently by Kosterlitz and Thouless. And of course, the easiest way to prove that there is a point where the qualitative behavior changes is to prove that for one value of beta, we have some kind of qualitative behavior. And for some other point of beta, we have a different qualitative behavior. So as soon as we find 2 points, beta, 2 inverse temperatures, at which the qualitative behavior is fundamentally different, then this proves that there's some kind of phase transition. So the most natural thing to do is to first say, okay, first we take beta extremely close to 0, and then we take beta to be extremely large, and we look if we can find some difference in the behavior. Okay. So first, let's have a look at beta very close to 0. Well, if beta is very close to 0, then the interaction strength is really small. So it means the spins really don't care if they point in the same direction or not. And of course, there's still going to be a correlation between neighbors because beta is small, but it's not exactly to 0. And also, yes, I didn't draw the graph, but of course the underlying graph is going to be just a square lattice. If I look at those two vertices, the spins still tend to have a small preference pointing in the same direction because they do not interact directly via an edge, but they interact indirectly via the other edges. Okay? So there's still going to be a positive covariance between edges that are far away. Right, so we look at the inner product between two vertices. But what you can show quite easily mathematically is that this decays exponentially fast in the distance. So what that means that, okay, you define this model on a finite box like this, but then you make the box bigger and bigger. You have a model on the infinite space. You take two vertices at a finite distance, and you measure how much do they align. And then when you increase the distance between the 2 points, this tends to 0 exponentially fast. So this is really, in statistical mechanics, this is the fastest decay that you can hope for. Okay, so this is the first part of the story. And of course, the second part of the story is to show that if beta is very large, we have a different kind of behavior. So if we were really reaching for only the existence of the BKT transition, the only goal would be to say, okay, now we take beta to be extremely large. And we ask, can we prove that in fact the decay is slower than exponential? Can we have a different decay type? Okay. So before telling you, okay, I mean, of course we already know that there is going to be some phase transition, otherwise it would not be so interesting to do this. But I first want to explain a bit what is the physical perspective on this problem. So how did physicists think about this? So, of course, here we have these probability measures. And this is an interesting object that you can study. But what physicists have been doing for a long time is that, in fact, they did not so much look at this probability measure, but rather at this normalization constant. So what they kind of said, and which turns out to be true almost all the time, is that if you can understand the partition function, then in fact this gives you a very good understanding of the model. So the partition function depends on two things. It depends, of course, on the graph, and it depends on the coupling constants. But in fact, we said we're going to just take all the coupling constants to be equal, and we just call it beta. Okay? And now you can ask, what are the properties of this function? So this is a function which depends on beta. And if you have a finite graph, it's easy to see that this dependence is analytic. But we are not interested in finite graphs. We are rather interested in the limit when you take the graph to infinity. So let's denote by lambda n. This is sort of the box of sides 2n. So this is going to be the set minus n to n. So this is kind of a subgraph of the square lattice graph. And you can look at the partition function on this subgraph. And, well, in fact, it turns out that it makes sense to consider the normalized limit of this constant. And the way to normalize is like this. You take the logarithm of this quantity and you normalize by the number of edges, the number of vertices. Okay? So this is a well-known quantity in physics, and this is called the pressure. So, okay, it's just a definition. And what physicists predicted is basically that you can see the phase transition by studying how many times you can differentiate the pressure. Now, what some physicists did was the following. They said, well, if this is an analytic function, then we can just calculate its derivatives at 0. And in fact, at 0, it means that everything is independent, and therefore calculations become very easy. So they said, okay, well, we cannot calculate all the derivatives, but we can calculate some of them. And then, of course, we're physicists, so we can just extrapolate and, you know, then we can guess all of the coefficients, and then we see if it's analytic or not. Now, basically what they predicted was that, okay, the function cannot be analytic everywhere, but in the same papers they also conjectured that other models had the same feature where in fact we believe that's just completely wrong. Okay? So if you study an analytic function, it's not enough to just find the first few coefficients and then extrapolate the coefficients. This is not a good strategy. Okay. But nevertheless, physicists, they had the feeling that there was something there. And they tried to come up with theoretical explanations of why this model had a phase transition. And in the end, what happened is that, well, as I will show you in a second, there are kind of two candidates for why this model had a phase transition. And Berezinsky, who was a Soviet theoretical physicist, first wrote a paper saying, okay, it's candidate number A. And then 1 year later, he wrote a paper about the quantum model, but in the sideline of the paper, he said, well, actually, this A doesn't have a phase transition, it's completely wrong, so actually it's candidate B. And the second time, he was right. And in fact, Kosterlitz and Thouless 1 year later, they weren't aware of this work of Berezinsky, and they basically also said, okay, this candidate number B, this is the phase transition, and we have a good explanation of why it happens. We can make a number of important calculations about the model, etc. Okay? And okay, to understand those two candidates, it's best to look a little bit at the Hamiltonian. So this whole business with the partition function, we're not really going to go into that very deeply for the moment. So remember that the definition of the Hamiltonian, okay, let's just completely forget about this J, we're just going to put a beta. The whole purpose of this Hamiltonian is that we're just summing over the edges of the graph, and at each edge we're just measuring the inner product between neighbors. So we take two neighbors at a time and we're going to look, okay, how much do they align? And okay, this is a function, and what do you do when you have a function? Well, you can study its local minimum, and then, you can study the global minimum, and then you can say, okay, how can we deviate from the global minimum? So of course, because we're measuring the inner product, the best possible situation is when all the spins are perfectly aligned. So this is called the ground state. So this is a global minimum of H. Right? So I mean, when all the spins align, you have the highest possible inner product, and you're the most negative. Now, of course, there are two ways in which you can deviate from the global minimum. Either you have some kind of local minimum, which is not a global minimum, or you're just sort of locally deviating from the ground state. Okay? Of course, we're not certain if they're local minima, which are not the global minimum. Okay? So the first way in which you can deviate is that you're just kind of like pointing approximately in the same direction, but not really exactly in the same direction. So this is kind of this is called the spin wave. And it's called, yeah, I don't really know why it's called a spin wave, but you can kind of see, like, the spins, they're kind of random. They don't, I mean, in the end, we have this Radon-Nikodym derivative, but we also have this Haar measure, so they always want to, like, have a continuous distribution. They're not always going to point in the exact same direction. And of course, there are also sort of local minima, which are not like this one. And what does it look like? Well, actually, it has quite a special structure. Yeah, this is not so easy to draw. But basically what happens is that it's possible that you have a face of the square lattice. And when you go around the face of this square lattice, the vortices make a full turn. So in this case, you can see that this is clearly not the global minimum because the spins are really not aligned. But if I just remove this vertex and you want to put it back in the minimal energy state, you're still going to put it like that. So they kind of keep each other in equilibrium away from the global state. So this is called a topological excitation. So what I want to stress is that, I mean, there are also other models of statistical mechanics, and I'm sure many people here heard about the Ising model. And in the Ising model, somehow the state space is different, so you don't have this circle, but you just have plus or minus 1. And what is a big difference between those two models is that S1 is somehow not simply connected. So the fact that you are not simply connected allows you to have these local minima, which are not global minima, right? You have the two-dimensional, okay, we think about the square lattice as sort of a two-dimensional plane. And you have these kind of punctures where the configuration makes the full turn. And because this thing is not simply connected, the spins cannot go, like if this is the complex plane, the spins cannot go in the circle. They have to stay on the circle. And this sort of stops them from reaching their global minimum. Okay, so now I'm going to say something that's almost true. So you have the spin configuration which is sampled from the model. And we can kind of see this as an independent product. Okay, so I put the equation in between the quotation marks. So it's going to be an independent product of the spin wave and the topological content. So actually this decomposition can be made rigorous by slightly modifying everything. But what it means is that we have those two ways of deviating from the ground state, but they're really sort of different objects that you can study completely independently. Okay? And yeah, the first observation is actually quite important, because what you can ask, maybe if beta is very large, this quantity doesn't decay at all, right? So it means that when beta is very large, even if I take spins which are very far away from each other, then they still want to point in the same direction, no matter how far they are, right? This is called spontaneous magnetization. And actually, what this spin wave part tells us already, so this is a famous argument called the Mermin-Wagner argument, is that this cannot happen. So what it means is that when you look at very large distances, those spins, even if they fluctuate a tiny bit, because they can fluctuate in a continuous way, they're going to still somehow make turns when you're far away from each other. Okay? So Mermin-Wagner says that there's no magnetization transition, and therefore sigma x, sigma y must decay in the distance. Okay, so yeah, I mean, for the people who have seen the Ising model, in the Ising model, when the inverse temperature is large, then you usually see one big cluster of plus or one big cluster of minus, and this is really different for the XY model. And in fact, okay, I don't want to go into details, but one way to see this spin model is basically you lift S1 to R, and then you get a kind of R-valued model, and then you can show that you have delocalization. Now, the topological content of the model is somehow very different in nature, because this continuous thing really doesn't play a role anymore. And it's in fact a discrete object, because at each phase we're no longer like measuring something continuous, but we're just counting, okay, does my configuration make a turn or not? So this topological content of the model, it's a completely orthogonal theory somehow. And what happened is basically that Berezinsky first proposed that the spin content of the model told us that there's no phase transition. That there is a phase transition. So he said, okay, look, we're going to look at the spin wave, these continuous fluctuations, and these continuous fluctuations, from that we can already read off from the partition function that this function cannot be analytic, and therefore you have a phase transition. But in fact, when we look at this model, the spin wave, you can lift it to R. And this is another model which is called the Gaussian free field. So the Gaussian free field is a Gaussian model. It has a covariance matrix. And in fact, when you change beta, you're just scaling this Gaussian process by a constant. So basically, this model is known not to have a phase transition. Then, well, Berezinsky and then later Kosterlitz and Thouless, they proposed that actually those topological excitations, they are responsible for this phase transition. Okay? So this is called a vortex, because in this case, the spin configuration sort of turns with the direction of the plane. But it's also possible that in fact the configuration turns in the other way. This is a little bit harder to draw. Yeah, actually I have no idea how to draw this, but it should look something like this. Oh. Yeah. So if you want to have fun, you can try it yourself. Yeah. So actually there's this very nice website online. I think it's called ventushki.com, but you can see the weather in the whole world. And then you can also see the wind, and you see some places where you have something which looks like a tornado. So if you see a tornado, this is a vortex. And then there are also some places where somehow the wind comes together and then it flows out in both perpendicular directions. This is called an anti-vortex. Okay? So, well, actually, we can ask how many vortices are there. Well, close to a vortex, it's clear that the configuration is really paying a lot in terms of the inner product, right? It's really far from being in a total equilibrium. So if beta is large, you're really giving a very low probability to things like this. But your space is infinitely big. So of course they will happen with some density, right? They will have, like, just if you flip a coin 1,000,000 times, of course you're going to see something like this sometimes. Now, you can ask not only, okay, how do the vortices work, but how do the vortices and anti-vortices work together? And it turns out that a vortex is much less costly if there's an anti-vortex nearby. So if you have a vortex and nearby an anti-vortex, this really greatly diminishes the energetic cost in the Hamiltonian. Now, if beta is very small, well, if beta is 0, for example, you really don't care about this effect. And if beta is large, then you care a lot about this effect. So really the vortices and the antivortices really need to help each other, otherwise they don't appear. And basically what these physicists propose is the following, namely that when beta is large, the antivortices and the vortices, they're coupled in pairs. Right? So they have opposite signs, you can think about them as particles, and they want to always appear together. Maybe not like next to each other, but really close to each other. And when beta is very small, they just don't care, and they just appear more or less independently. Okay? And, okay. In general, physicists are extremely smart, so of course they were able to predict all kinds of things using this formalism, which we think is true, but still we don't know how to prove it. Yeah. By the way, I wanted to do a break at half time, so I'm just going to continue for a bit longer. And if there are any questions, please ask, okay? Because it's nice when...
So the transition is due to this topological term, and because you said that the Gaussian-free field, you said something about the Gaussian-free field.
Yes.
So inducing any phase transition.
Yes.
I didn't quite get that, but it is very two-dimensional.
No, this is a very nice question. So the here you have the GFF. Okay, so actually we can see it as e to the I times some constant. Let's call it alpha, and then you have the GFF. So here h is the GFF. Right, so you have a real valued thing, and then you do e to the I alpha h. Alpha is a constant which depends on beta. But this dependence is entirely explicit. So if beta is very small, then there's almost no interaction, and this alpha is going to be very large. And if beta is extremely large, then you don't want to fluctuate so much, so this alpha is going to be much smaller. But yeah, like somehow the dependence of this model is completely like, right? You're just changing alpha, and it's like, so this part really has no phase transition. And by this reasoning, just by elimination, the only possibility is that the topological thing is responsible for the phase transition. However, in the end, we're not really going to prove the existence of the phase transition through this decomposition. So in fact, we're going to decompose the model in an entirely different way. And then on the other side, we get another model. And in that model, we're going to prove the phase transition. And then we're going back to the XY model. Okay, so we'll see it in a sec. So are there any other? Yeah. So, yeah, like I can try to explain it, but the problem is that it's really difficult to draw. So here what you see is that when you follow the phase, the configuration moves in the same way. So there's a certain orientation, which in this case is positive, because when you follow the thing, yeah, it looks the same. Well, now imagine that I just flip the plane, right? So I flip the spins on the left and right, but I keep the spin values the same, right? So if I really, okay, if I do the flip, then it looks something like this. This one goes there, right? So it will point that way, yeah, that way, right? So I mean, mathematically, there's not a big difference because I just flipped the two things. Like they really have the same role. They're just sort of the symmetric counterpart to each other, but just visually it looks very different. Okay? I don't know if it explains your question. But what's important to see is that no matter how we assign the signs, the vortices and the anti-vortices have a sign, and it's plus or minus. So they, yeah, you can imagine them as being sort of, if you like the physics intuition, they're sort of charged particles which attract each other. Because when they're closer together, the energetic cost is lower. Are there other questions at this point?
I didn't get the exposition sigma xy equals sigma spin to logical. What do you mean?
Yeah, so I'm going to say what I mean, but I'm not going to prove it. So what I mean is basically that you can create two models which are independent. So you take independent samples. And if you do this in the right way, then you can create a model here and a model here. And if I take independent samples and I multiply the spins, right, we're working in this group. Or rather, okay, S1 to the power V if you want. Then you get this model.
And what is the relation with the GFF?
So this is the GFF.
Oh, sigma spin.
Yeah, it's just the GFF, except that you don't look at H, right? H is R valued, but rather you look at e to the I alpha H.
Okay.
Yeah.
Oh, okay.
So, yeah. So are there any other questions? Okay. Right, so I think one interesting detail about this story is that we have this physical intuition and, well, we think everything is correct, but somehow the mathematical proof goes via a route that's entirely different. Yeah. So to see what's going on, we're going to do some calculations on the board. But I'm really hoping to try to convince you that, in fact, those calculations are not so hard in some sense. But still so hard that I need to look at my notes. So recall that the definition of the Hamiltonian, for the Hamiltonian we sum minus 1/2 beta times yeah, I think it was like this. The inner product. And in fact, the definition of this in the complex plane, this was just equal to minus beta sum over xy 1/2 sigma x sigma y bar plus sigma x bar sigma y. Okay? But notice that here we're summing over edges, and we can just as well replace it by directed edges, because here we have this symmetry which we can just get rid of. So this is just minus beta xy in directed edges sigma x sigma y bar. Oh yeah, and there's of course the factor 1/2. Okay. So recall also that we defined the expectation functional such that when we calculate the probability or the expectation of some observable, this is by definition equal to a of sigma e to the minus 2h beta of sigma d sigma. Okay? And before you're interested in the inner product between two spins, but in general you can put anything here, right? But the most fundamental thing that we are interested in is the partition function. So the first thing that we want to do is to understand the partition function. Well, the expectation of 1 is 1, so then this whole term disappears. So z of beta, this is just equal to e to the minus twice the Hamiltonian, but that is just beta times the sum over the edges. Okay? So now there's a very brute force way of doing this calculation, and that is just we expand all the exponentials. So of course, this sum is in fact a product, right? The sum in the exponential is just a product. And therefore, we can just write this as, oh, that's wrong. So basically, this drops out as a product. So in the end, we're just expanding an exponential for every directed edge. Okay? So this step, really the only thing we're doing is we say, okay, we take the sum within the exponential, we take the sum outside, we get a product. So we have one exponential for each directed edge, and we just expand each of those, right? So for each directed edge, we get a number n, and then we take beta to the nxy over nxy factorial, right? And this part of the thing goes inside the integral, right? So we kind of separate all the content that doesn't depend on sigma, and the stuff that depends on sigma we put in the integral. Now, in fact, this integral, this is the Haar measure on all configurations. So it means that if this is our graph, then this Haar measure, what it does is that it really applies independent spins to each vertex. It's really completely independent. And in fact, the integrand also decomposes as a product over the spins. Right? You can just count okay, for my vertex v, how often does it appear? And that's it. Now suppose that I have some vertex v, and this vertex v appears k times in this integral, so it's sigma v to the power k. And then I calculate its random position in this higher measure, right? So let's calculate, for example, sigma v d sigma. So then what I'm doing, I say, okay, I pick a random spin and calculate its average position. Well, of course, its average position is going to be 0. And in fact, if I raise it to some power k, then this is going to be just 1 if k is equal to 0. So in fact, because you have an independent product, the only way that this integral can be non-zero is if the integrand is in fact identically equal to 1. So this whole expression, we can completely forget about this integral. And we just want to make sure that all those things, they cancel out, okay? So in fact, how do we count, for example, the number of times that some sigma v appears? Well, it can appear positively if it appears, as a v, some other vertex, but it appears negatively if, it appears in the other way. Right, so I'm just going to introduce a new definition, which is called the source function. So this is a function on the vertices. And it just, well, I will give some meaning to it in a second. Okay. It literally just counts the number of times it appears in one way minus the number of ways it appears in the other way, right? And if this source function is identically equal to 0, then we know that we have a contribution of 1, and otherwise we have a contribution of 0. Right? So this is a very important formula. Okay. So what is n? Well, in fact, we say that n assigns a non-negative number to each directed edge. And in fact, we think about n as a random multigraph. Okay? So, okay, what we imagine that n is, well, if we fix some n such that this condition holds true, then it's basically a directed multigraph which is sourceless, right? So by sourceless we mean that at every vertex the number of arrows going out is the same as the number of arrows going in. Okay? So this, this condition just naturally appears in this context. Okay. So in fact we can say a bit more. I mean, okay, I'm a probabilist, and I think some people in the audience are also probabilists. And what we see here is in fact the weight of independent Poisson random variables. Right? So if you have the weight, okay, some constant to the n divided by n factorial, this you can interpret as a Poisson random variable. So I'm now going to rewrite this in a slightly different way. This is the same as n of beta. So this is a probability measure with, I will define it in a second, of the event the d of n is equal to 0. Okay? So of course, what is n? Well, n of beta, this is IID Poisson random variables, but not normalized. I mean, if we have a Poisson random variable, then we know that the weight of a certain outcome is in fact e to the minus beta times this. But I just want to forget about the e to the minus beta. We just have a Poisson random variables, but without the normalization. Okay? So it's IID Poisson random variable, not normalized on the directed edges, with weight, parameter beta. So really, if we want to understand this partition function, what we're asking is, okay, I sample IID Poisson random variables on these edges, and now I look at the probability that in fact the graph that I get is sourceless. It satisfies this sourceless constraint. Now, in fact, this really doesn't rely on the dimension that we work in. But now we're going to introduce something new where we really use the fact that we are in 2 dimensions. So in 2 dimensions, you can define the winding number of the yellow path, right? So for example, if I put myself outside of this graph, then of course there are no arrows which wind around this thing. But if I put myself here, then you can see that there's sort of a total winding of 1 around the point. So, yeah, why is this the case? Well, I can sort of, if I walk over in R2 from this face to this face of the graph, well, I encounter 1 yellow arrow, so it kind of means that I'm going to do +1. So this kind of defines a height function, but what you want to see is that if you take another path, you're still going to arrive at the same value. So in fact, because you have this sourceless condition, you know that the way you construct this height function is independent of the thing. So I'm just going to give some other example. So if we imagine something like this, then here, okay, you see that there's a total winding of 0 here. Here there's a total winding of +1. Here there's also a total winding of +1. And here there's a total winding of -1. Right, so for example, if you go from this face to this face, there are 2 yellow arrows which are coming from the right, so it means that you're going +2. And you can make this picture consistent because of this sourceless constraint. Okay? Now, the partition function of the model is equal to this quantity. But what I can also do is I can look at the conditional measure where I condition on this number. Right? So I look at condition that I see a sourceless thing. What does it look like? Yes, yeah. So I mean, this is not a probability measure, but now when we do the conditioning, we also normalize. Okay, so this is a probability measure. Yeah. So what is the definition of this measure? Well, this is just by definition m beta of the thing, indicator dn0 divided by, well, it's the partition function, right? So this is the definition of the measure. Yeah, so in this probability measure, n is random and it's sourceless, right, by definition. So this function, in fact, becomes a random function. And this is called the height function. So h is a random function called height function. Okay. And in fact, it's not only a random function. In fact, the partition function of this model is the same as for the xy model, right? Because when we normalize, we're using the same normalization constant. So there are two models which are, it's not really clear how they are related, but they have the same partition function. And, well, like I mentioned at the beginning, physicists believe that everything is already contained in this partition function, right? So all the information is contained. And in fact, it also means physically that the two models should have the same phase transition. So if this xy model undergoes a phase transition, then this height function should also undergo a phase transition and vice versa. Okay? So this correspondence is already known for a long time, and in fact, it was proved by Fröhlich and Spencer in 1981, that both models have a phase transition. So for both models, you can show that, well, there's this exponential decay phase and a phase which is looking differently. So what they prove, yeah, both models have a phase transition. Yeah. So in yeah, what is particular about their proof is that their proof really used this thing where you say, okay, how do I prove a phase transition? Well, if at very low beta it looks different at very high beta, then I'm done, right? So this is really an analysis of beta, which is really much larger than 1. So yeah, during my postdoc, I also thought a lot about this height function, and later I also became interested in this xy model. And in the end, it led to a completely new proof of this fact. So it still uses this correspondence, but after that, the analysis is completely different. And one big difference is that the analysis, like in my analysis, somehow you can even say that the two phase transitions occur at the same beta. So to show that the phase transition occurs at the same beta, well, you have to say something which is not perturbative. And somehow the methods that, well, that I used, which were developed in maybe the 20 years before, they are somehow not so precise, but they work really well in the non-perturbative regime. So they work well for all beta. Yeah. So I think actually this is a good moment if we take a, yeah, let's take a break until 3:12. Yeah. Okay. So I propose we start again. So in the first part, we saw that we have this xy model, and there's this physical explanation about why there should be a phase transition, and we saw that at least for the partition function, there's a link with this new model, which is a height functions model. So in this model, h is a random function from, in fact, the faces of the planar graph. 2z. Okay? So, like I said before, this only makes sense for planar graphs. So the fact that we are in 2 dimensions is extremely useful. And it's an integer valued model. Okay? Now, I just want to explain one way to think about this, because, let's go to white. We all know that the Fourier dual of the circle is z. Okay? And of course, in the initial model, the model was defined as a circle-valued model. But now we've transformed the model into a z-valued model. And I mean, okay, of course you can think about this for a long time and then it's just yes or no, but maybe you could say this is not so strange. And I want to make the analogy a little bit further. So, okay, I'm just putting it in quotation marks. We can also look at this model for different betas, right? So we have this measure where we sample these Poisson random variables, but then we condition on this event that this multigraph is sourceless, like here, right? So this is the multigraph, and they have the height function. Now, in the XY model, if beta is very large, then it means that all the spins align, right? So there's very little flexibility in the XY model. But on the side of the Poisson random variables, it means that the Poisson random variables a priori have a very high intensity. So they tend to take very large values. And in fact, what we shall later see for this height function is that this height function tends to fluctuate quite a lot. On the other side, if we put beta very small, then in the XY model, the spins are almost independent. It's a super high temperature. But if beta is small, the intensity of the Poisson random variables is small. So in fact, the random variables really prefer to be equal to 0. And it means that this height function is very stiff. So you can kind of see this as a form of the Heisenberg uncertainty principle. Okay. So of course, for those who know the Ising model, you can also do this for the Ising model. And in the Ising model, the group that you work on is the group z over 2z. And in this case, you can do the exact same analysis, and you will also end up with a model whose values take, whose spins take values in the Fourier dual, and this is going to be z over 2z. And in fact, this is really cool because it means that the dual of the Ising model is again the Ising model. But, okay, of course, it's the Ising model, but on the dual graph, right? So the first Ising model was defined on the vertices, and the second Ising model is defined on the faces. But of course, when you're on the square lattice, the dual graph is the same to itself, right? So it's really the same model. But you still have this thing which is called, which is the Heisenberg uncertainty thing. So if you have a temperature here, which is T, or rather a beta, then here on the right you have kind of a dual beta, which depends on beta. Now, what this Fourier transform business tells us is that in fact, when beta is small, the dual beta has to be big and vice versa. So there's kind of like an inverse relation between beta and beta star. Now, of course, if you're a physicist, this actually allows you to already make some predictions, because if you believe there's only one phase transition and that you can see this phase transition from the partition function, then this must just be a solution to the following equation. Right? Because the two models have the same phase transition, there's only one beta for which it can occur, so it must be the self-dual point. And in fact, in 2 dimensions, it is possible to solve this equation. I mean, this formula is in fact very simple. And this is also the critical point. So this physical intuition is correct. Now, of course, we can ask, right? So actually, beta critical equals the beta star of beta critical. So in fact, of course, we can ask the same question here, but the same reasoning doesn't work because the dual model is not the same model, right? The dual graph is the same graph, but they take values in a different space. And therefore, there's no you can still define this, but it doesn't have any special value. It's not a special thing. And actually, okay, let's say a little bit more. So I'm not expecting that this is completely clear, but just for the people who know the Ising model, this duality transformation, so it like kind of interchanges the two sides of the phase transition. And it means that fundamentally there's a relation between the subcritical and the supercritical phase, right? And this is, okay, I'm not giving any details here. So in fact, you could say subcritical, so that's the phase there. This is a little bit like the supercritical. Now, of course, this could still be true for this model, right? It could be the case that, you have some kind of beta critical. And it could be the case that the behavior here is more or less the same as here. But this is completely not the case. Actually, for the Ising model, here the behavior is special, and then, okay, here it's all a bit the same. And here what happens is that here, so for low beta you have exponential decay, right? And this doesn't include the critical point. And then above the critical point, in fact, the model looks a little bit like at criticality. So for larger values of beta, like there's qualitative change in the behavior, but it looks way more like the critical point than like the subcritical regime, right? So the fact that the Fourier dual is not itself really makes, in some sense, the model richer, at least in 2D. Okay. So I think I have about 30 minutes left, because I'm not going to use this opportunity of keeping you here forever. So what I want to do is to explain a little bit like what is in the, how does the proof work in the very broad sense. And then if there's some time, I will start explaining a little bit what's going on. So for step one, we're going to only look at this height function. So we really don't care anymore about this, about this xy model. We're only going to look at the height function. And let's say that we fix beta, but we fix it to be very large. So very large, it means that in the xy model it's very rigid, but the height function a priori likes to fluctuate a lot. So we put the model on a large box. By the way, are there any questions about what, the previous bit? Right, so remember this is just this lambda n box. So we fix beta, and we are going to look at the height of the square, which is more or less at the origin. So this is the height of 0, 0. And now we ask, what is the variance of the height at 0, 0, as we take n to infinity? So, okay, what's the variance? What's the variance in this measure m, which depends on n and on beta, and it's this thing that's normalized or conditioned on being sourceless. So, okay, I'm skipping some details here, but in the first part of the proof, I proved that this variance goes to infinity. So that this is equal to infinity. So when beta is small, the height function is rigid, and what you can prove quite easily is that when you take boundary conditions far away, the height function still stays very close to 0. But here what we prove is that when beta is very large, this variance in fact blows up. So this is the phase transition for the height function. So for low beta, okay, let's give this a name. Yeah, so let's call it maybe m, which only depends on beta. So it's really the limit of this variance. So for low beta, m of beta is smaller than infinity. And for large beta, m of beta is equal to infinity. So for the people who know the Gaussian free field, if we are in this regime, it's expected to converge to the Gaussian free field. This is really not proved, except in some very specific cases. Okay, so this is the first step. So we have established that there is a phase transition in the height function model. But of course, we care about the xy model, right? We want to show that, in fact, we can use this theory to say something about the xy model. So, yeah, actually I did my entire PhD on height functions. So height functions are my bread and butter. And well, when I found this result, in fact, I liked the result, but I didn't know if it had applications. I think, of course, everyone likes their own results, right? So, and in fact, well, I was extremely lucky because other people understood that this could actually be used to prove the BKT transition in a new way. So there were two teams, Eisenman. Yeah, I'm reading it from the paper because I know the names, but I'm extremely bad at alphabetic order. So I always mess this up. So Eisenman, Harel, Palette, and Shapiro. And then at the same time, Van Engelenburg and Liz. So, okay, this is 2011. So what they proved independently is that if you have the delocalization of the height function, then it implies that this xy model is in what we call the polynomial decay regime. So it's not magnetized, but it's also not exponential decay. So they proved that you have this one-way implication. And okay, it means that, yeah, there's some relation between the critical beta in the two models. Yeah, but in the end, what I was able to do, I was able to go a little bit further by proving that, in fact, the phase transition happens at the same point. Yeah. I'm also extremely bad at managing space on the board. But so step 2. So of course on the xy side we said we have a phase transition when we exit this exponential decay regime. But on the height function side we define the phase transition at this point in an entirely different way. So it's completely unclear how this relates to exponential decay. And in step 2, I proved basically that this phase transition coincides with the exponential decay phase transition. So this is called sharpness of the phase transition for height functions. So what does that mean? It means the following. If this function is localized, so as soon as you go far away, then the variance still doesn't blow up, right? The height function is so rigid that it always likes to stay close to 0. If this is the case, then, I mean, of course, here we study the variance, right? But we can also study the covariance. And the covariance, which depends on n and beta of hx and hy, then this quantity decays exponentially fast in the distance, right? So I fix 2 points, maybe I fix those 2 faces, and I look at the covariance of the height function. I know the height function is in this rigid regime. And now I send the boundary conditions to infinity, but I keep looking at those 2 faces. Then what we know is that if things don't blow up, then this limiting covariance decays really, really fast, right? So somehow the model doesn't manage to communicate over large distances. Are there questions about this step? Yeah. So by boundary conditions, in this case, I just mean the size of the system, right? So it's just this n. No, so I mean, in this model, the boundary conditions are kind of naturally 0, because in this definition of the height function, I look at the winding number of this multigraph. And by definition, if you're not surrounded by the graph, your winding number is 0. And then when you're in the graph, you're just counting. Does it answer your question? I mean, okay, I didn't really want to go in the details of the height function, but you can really think about it as having 0 boundary conditions.
Sorry, something like, how do you know that below a critical value it's going to behave the same way and above the same? Because you could have 2 points where it behaves differently, but how do you know this?
Yes. Yeah, so this is a very good question. In fact, we have now 2 models, so we can ask the question for both models. For the XY model, there's a monotonicity, which tells you that the covariances are always increasing. And this sort of defines the critical point. On the height function side, we don't have this monotonicity, but it follows as a corollary of basically what I'm going to present now. So what is the last step? So step 3. So first observe if there is exponential decay, then you can identify the decay rate. Okay? So I keep it a bit vague because in fact this is true for both models. If you have exponential decay, then you can ask how fast does it decay in the distance. In the XY model, you look at the expectation of the inner product, which is the covariance. And for the height function, you also look at this limiting covariance and how fast does it decay. And of course, and we call this the mass typically. So the mass of the model. So you have a mass of the XY model for a given beta, and you also have a mass of the height function for a given beta, right? So it's just a number which depends on the model and on the inverse temperature. And if there's no exponential decay, then the mass is equal to 0. Right? So just saying, okay, if you look on the scale of exponential decay, there's no exponential decay, so the decay rate is 0. Now, is there a question? Or? Okay. So what is the last result? The last result which I'm going to present is that, in fact, there's a direct relation between those two masses. And in fact, the mass of the height function, height beta, this is twice the mass of the XY model. Okay? So the decay rate in the height function is always twice as fast as the decay rate in the XY model. But most importantly, this is 0 if and only if that is 0, right? So we have this relation, but the most important is that they're 0 at the same time. So in the XY model, it means that we have identified the phase transition, because by definition, it is the point where you lose exponential decay. And on the height function side, well, we know that the exponential decay phase transition is at the same point as this fluctuation phase transition. And for this fluctuation phase transition, we already showed that it existed. Okay? So the first step, together with any of those two articles, tells you the existence of the BKT transition. But in this second step, you get a better picture of the phase transition on the height function side. And then by doing a different kind of analysis on those height functions, you can show that, the phase transition must coincide. So I think one important comment to make is that, physicists in the beginning really approached this problem through the partition function. And in fact, we also saw that the partition function plays an important role in understanding the relationship between the two models. But in the end, nowhere in these results we say anything about the partition function. So we really established the phase transition as, okay, there's really some qualitative change in the probabilistic behavior of the model. Of course, we would like to say that we can also see this on the level of the phase of the partition function, but at the moment, we don't have an idea on how to do that. Okay. So, are there any questions about this this proof overview?
Did you mention anything about the low beta regime where the m beta is finite, or is it easy, or?
Yeah. So that's a very good question, because I only focused on large beta in what I said before. Like the arguments to show that for low beta you have this flat behavior or that it's completely decorrelated, those are not super easy arguments, but it's now kind of standard. So you have the Peierls argument on the height function side, and then on the XY side there are certain correlation inequalities which tell you the result. So when you do all this machinery, you will also get this, but it's more as a side thing rather than, But yeah, for small beta, so it means that the XY model is very decorrelated and the height function is very rigid. Here you can, it's quite straightforward to prove that things are sort of flat.
Related to this question, do you have a decent Hamiltonian for the height field? I mean, just because the way you constructed it is kind of indirect, but let's say the Peierls argument usually they really use, I mean, like the Hamiltonian associated to the H.
Yeah.
Is there something, I mean, like can you write it as a function of H, or you need
Yeah, so the height function that you get, I mean, I completely didn't give like a nice definition of this height function, but it's quite easy to write down a good definition of the height function. And this we're also going to do next week. So yeah, there's another way which is much more simple to define the height function, and then you can see that this height function has certain nice properties, etc. And then you can do this Pauwels argument where you say, well, it's very costly to have a height difference, so in the end there won't be large patches where I'm non-zero. Any other questions? Okay. Yeah, by the way, I didn't mention it, but I'm trying to write some lecture notes and put them on the website. So it's just my personal webpage. Yeah, everything that's presented today is already on there. And I try to update them every week. Okay. So, yeah, I think the step which I like the most is the first step. And this is the step which I'm going to try to present next week. And in the remaining time, and probably the beginning of next week, I'm going to explain some important tools which are going into this proof. So this is machinery which has been around for quite some time. Okay, so let omega denote a partially ordered set. So we say a measure. So actually it's a probability measure, satisfies the FKG inequality if let's call it P. Or yeah, let's call it mu actually. If mu of Fg, I'm going to explain this in a second, is larger than mu of F times mu of G. For any increasing bounded functions f and g. Okay? So we have a partially ordered set. I'm going to make this very concrete in just a second. But we have a partially ordered set, and we have a notion of increasing functions. So it means f and g are functions from omega to r. And we have a notion of increasing functions. And now we say that we want increasing functions to be positively correlated. So FKG stands for 3 mathematicians. So they are Fortuyn. Cool. Fortuyn, Kastelein, Genebra. So what they did was that they wrote an article where they explained how you can derive such an inequality. So suppose we have some mu, then they were able to say, okay, if mu satisfies these conditions, then you satisfy this inequality. And it's important to mention that actually before this inequality was already proved for a smaller class of measures. And in this case, it's called the Harris inequality. So I mean, okay, now everyone in the field kind of calls it the FKG inequality, but yeah, you could also call it the Harris for time Kosterlitz-Geneva inequality if you want, but okay, we stay with what is being done historically. Okay, so what does this mean, for example? Suppose you take this height function. Then what we said, okay, we take a very simple example. We take this as a graph. We say that sort of, you sample the Poisson process, etc. And then you ask, okay, what does this height function look like? So in general, for the Poisson process, the neighboring things don't like to be far apart, right? So if you have two neighbors, if here the value is plus 1,000 and here it's minus 1,000, then it means that there are like 2,000 arrows going down at least, right? So every time you make a large height difference, you really force there to be a lot of those Poisson edges. So what does this mean? This means, for example, that if this value is high, I also expect that this value is also high. And what you can prove, for example, is that if we have this M measure, so okay, I'm not going to write a conditioning event, but if this is the phase 1 and this is phase 2, then the height at phase 1, height at phase 2, this is greater or equal than mn beta of h f1, mn beta of h f2, right? So it means I'm just taking the expectation of some random variables, right? So omega is the set of all height functions. This is just a random variable which takes a height function omega and assigns it a real number. And now, well, what I'm kind of claiming is that in this case I have a positive association. Okay? So in general, this FKG inequality is an abstract way of thinking about increasing functions until they're positively correlated. And it turns out that this inequality does not, in general, give you extremely precise results quantitatively, but you can use it extremely well to get qualitative results, even at the transition point. So for non-perturbative theory, this inequality is extremely important. Okay? Actually, I mean, in the proof I had 3 steps, but in the lecture notes I will have, I think, 4 sections. And the first section will just be about this inequality. Okay. So I want to explain some results, and I could explain them in the largest generality, but rather I would like to explain them in the context of percolation. So this is really a different probabilistic model, which is very simple. We start again with the square lattice. And now we're going to color every vertex yellow or red, right? And we color them in a random way. So with probability P, we're going to color them yellow. And with probability 1 minus P, we're going to color them red. So maybe it looks something like this. So it's really, okay, for example, if P is 1/2, then we can imagine that we really just have a coin. And for each vertex, we flip a coin and then we decide if it's yellow or red. Okay? Now, okay, to make it a partially ordered set, we're going to say that yellow is 1 and red is -1. So the state space is just going to be plus or minus 1 to the number of vertices. And this is a poset. So just a standard partial ordering on functions, right? Just its pointwise domination. So this measure, we can give a name. We can call it PP. P is the parameter. And okay, I'm just putting now as a theorem, which in fact is due to Harris. Yeah, so what is the theorem? PP has the FKG inequality. Okay, of course he didn't call it the FKG inequality because actually his paper was published before, but just for clarity, I will call it the FKG inequality. And let's look at some examples of increasing functions. Okay? So for example, I can look at the indicator of the event. I can walk from left to right using yellow. Okay? So I claim that this function is an increasing function. So why is it an increasing function? Well, suppose in fact that I can walk from the left to right using only yellow steps. So for example, if it looks like this, I can walk from left to right using only yellow. Now if I change some more colors to yellow, clearly I can still walk from left to right using only yellow, right? So these type of events are called increasing events. And the Harris inequality tells me that if I take two increasing events, then they are positively correlated. Okay? So I think because we have a couple of more minutes, I want to show a very beautiful theorem and hopefully also do the proof. And this is somehow the heart of step 1. So there's a theorem which is already known for a long time, which tells us something very specific about these kind of measures. And this we're going to use next week to prove the delocalization. So this theorem is known as Zhang's argument. And what does it say? Consider, I'm not stating it in the largest possible generality, but just consider PP on which graph? We're going to do it on the entire square lattice, right? So it's really infinite. What does it say? It is impossible that the probability that there exists a unique infinite yellow cluster is 1, and the probability that there exists a unique infinite red cluster is 1. Okay? So if you take the square lattice, and for each one I make it yellow or red independently with the same parameter, it's impossible that both the yellow and 1 have a unique infinite cluster. And we're going to use for this the FKG inequality. So notice that, of course, it's possible that both have an infinite cluster. It's even possible that they both have a unique infinite cluster. But in this case, I mean, if there's a unique infinite cluster, if you kind of look, oh, that's the wrong color. If you look at what those clusters have to look like, right, because they're both unique, they kind of need to have a sort of infinite tree structure, right? I mean, both, they kind of permeate the whole space. And because they're unique, they can't cross each other, right? So they need to do this very kind of weird finger thing. But this result kind of tells us that this is not possible. And to make it extra fun, I have only 3 minutes to explain the proof. Okay, so we let epsilon be very small, but in fact we can just take it to be equal to 1/7. And, well, we know that there's a unique infinite cluster, right? Of course, we're going to argue by contradiction. So we assume that this measure exists, and then we derive a contradiction. So now, if there exists an infinite yellow cluster, if I make my box really large, then this infinite cluster intersects the box with a probability of almost 1. So choose n large enough such that the probability that if this is like 2n by 2n, the probability that this is connected to infinity is larger than 1 minus epsilon to the power 4. And in fact, I can make n so large that the same holds true also for the red cluster. Right? So I mean, this is just because there's a unique infinite red cluster and a unique infinite yellow cluster. If I look far enough away, I will see both of them. Now, the probability that yellow is connected to infinity is an increasing event. And it will have to leave the box somewhere, right? And in fact, what it means is that one of those 4 sides is connected to infinity, even if they're not allowed to use the connections inside, right? So for example, if this thing does something like this, then okay, if I want to go from here to infinity, I leave the box there, but then I re-enter, but at some point I don't come back, right? So really this side is connected to infinity. Okay, but anyways, we have to find this event. So what I claim is the following. The probability that I connect to infinity using only the right-hand side, this is at least 1 minus epsilon. Okay? So I say, now I want to go to infinity, but I only use the right-hand side of this box. Okay? So I'm just going to assume this claim for now and then derive the result. And then I think it's good if we maybe stop, and then I will quickly say one more sentence. So, of course, if this happens, the probability of the following event is going to be 1 minus 6 epsilon, at least. Oh. So this is the event that the right-hand side is connected to infinity via a yellow path. The top is also connected to infinity via a yellow path. The left also, and the same for the red. Okay? And why do we get this bound from the claim? Well, it's just the union bound, right? So the complementary event has a probability which is smaller than epsilon. Well, we're doing 6 things here, so we just get 6 times epsilon. So this is equal to 1 over 7, which is strictly positive. However, we know that there's one infinite red component and there's one infinite yellow component. But if you look at this picture, there's no way to connect those components without crossing, right? I mean, remember, we're on the square lattice, so the yellow component cannot cross the red component. But now if I'm trying to connect, like, okay, maybe I could try to connect, like, okay, maybe this is connected here. But that's a contradiction, right? Because this component is infinite. We can try to connect it on the inside. But now it's kind of strange because those are not connected and we said that there was only one infinite red component. So what you see is when you have this event, there's no way of connecting all the red and all the yellow without creating multiple components. Okay, so this claim, you can derive it actually immediately from the FKG inequality. Because if this is connected to infinity, you can write it as a union of 4 events, namely it connects via this one, this one, this one, and this one. All 4 events have the same probability. And then, yeah, using the FKG inequality, you can go from 1 minus 4 epsilon to 1 minus epsilon. So, okay, maybe we'll do it with a bit more patience next week, but this is it. Thank you.